So, welcome to today's lecture, and while we have done in the earlier classes on some of these introductory versions of convolutional neural networks and trying to get down into what is an abstraction of trying to understand a deep convolutional neural network. Here today we would be starting with something called as a VGGNet. That's a short acronym for the group from where it originates out. So, this originates out from the visual geometry group, and that's where the name comes down as VGG. So, while in the earlier lectures we had already studied about how the different characteristics of the network as well as the architecture and how it's linked out, how the data flow happens down. Today what I am going to do predominantly is actually to go through this whole set of codes over here, which will be showing you how this whole architecture is implemented, and then the learning as progresses through it. Okay. So, let's just go through how it works out. So, the first part of here is just a set of your header files which we are going to use for all the purpose. So, I am just it is the same set of headers which are present down in all the earlier codes which we are going to reuse over here as well. Now, if you see that this is a run version which I am using, and one of the reasons is that this network being quite deep, it takes us substantial amount of time in order to compute if we are just going to run through the epochs. That runs in a few minutes, in the order of a few minutes actually, typically about 15 to 20 minutes over there, and in order to keep it just precise and within the time limit of our recordings, I am just using a network which is already trained out, and the states of it which is preserved over here. So, that does not change anything from your side, because you will be provided with an untrained network over there, which you will have to actually start training it from the scratch, and then you would see how the network gets trained and its performance increases over there. So, this is the first part of it, which is just my header files over there, which I need to copy down for my library calls, whichever I want to do. The next part is to go around and do with the data. So, on my data what I use is the standard CFAR. So, as in you had seen in the earlier lecture on AlexNet, where we had although AlexNet was trained down for ImageNet kind of classification problems, which has 1000 categories in which you have to classify, and all the images are of size 224 cross 224. So, here we are going to use down CFAR, and since the images are of size 32 cross 32, so we need to rescale it out, and I am using the same kind of a transformation scale factor over here, which will be applying the transformations on the data which is getting loaded over here. So, that is just to keep it aligned with what we have done in the earlier one as well. And now that is just my train loader and my test loader. So, both my data files get loaded over there, and then you see that the files are present. So, it is verified, and finally we run down and check down what is the total number of samples. So, that is quite same as we had for our CFAR 10. So, 50,000 images on the training sample over there, and 10,000 images for my testing, and that is with what I am going to start working on. Now, you had seen down in AlexNet it was quite easy, because you could actually call down your models over here, and that is a library within Torch Vision. So, within Torch Vision you have a definition architecture over there available within the function called as models. So, here I just need to invoke my call to VGG16. Now, VGG16 is basically that layer which has 16 learnable parametric layers in total, and then that is the one which we are going to use. So, once we have this model loaded down, and then I can print and look through it. So, if you see through it, you would see your it is sort of like one by one blocks which are connected down as in your VGG. So, the first block was a battery of 2 subsequent 2D convolutions, and finally after that you have max pooling operation coming down, and then again 2D convolutions. So, the first one is what converts down from 3 channels onto 64 channels. So, that is the battery of filters which you have within the first convolution layer. Each filter is of size 3 cross 3 with a stride of 1 and a padding of 1, which means that whatever is the size of the input which goes over here, the same is the size of the output which comes out from this 2D. This is what happens in essence over here. Now, then you have a nonlinear function which is ReLU, and subsequent to that you again have a 2D convolution which maps down 64 layers which come as an output from the earlier 2D convolution onto another 64 layers. So, there are 64 such unique kernels which get defined over here, and your kernels are again 3 cross 3 in the spatial size. It has a stride of 1 and a padding of 1 as goes down. Okay. Good. So, in the next version what I do is we have ReLU again put down as a nonlinearity, and then you have a max pooling operation coming down over here, which is the 2 cross 2 max pooling, and then subsequent to that we have a 2D convolution, and then again a ReLU, and then again a 2D convolution, and then a ReLU. So, this is the second battery which comes down, whereas this max pooling has now reduced down the size by doing a so it uses a max pool kernel of 2 cross 2 with a stride of 2, and for that reason it just reduces to half of the size. So, from 224 cross 2 to 4 which was the spatial size at the output, from here you get it reduced to 112 cross 112 at the result of this particular block which is being called down, and then that 120 so 112 cross 112 sized image is or that block over there. So, there is its 64 number of channels and 112 cross 112 is the spatial span over there. Now, that is again convolved with 128 unique kernels in order to get down 128 channels or slices coming down on the output. Each kernel is of size 3 cross 3 with a stride of 1 comma 1 and a padding of 1 in place, and then you have your ReLU coming down as a nonlinear function. Now, we do not have any further max pooling over here, but that again succeeds by another battery of 128 convolution kernels, each of size 3 cross 3 and stride of 1 comma 1 and padding of 1 comma 1. So, that would mean that the resultant of this one is also of a spatial size of 112 cross 112. Subsequent to that, you have your ReLU and then a max pooling which brings it down to half of the size. So, that makes it 56 cross 56 because of the size and stride, and then you keep on doing that. So, over here you again have in the next battery you have 3 convolution kernels which would come down, and subsequent to that you have your next max pooling. Now, following that you again have 3 convolution kernels coming down over here and then a max pooling. Subsequent to that you again have 3 convolution kernels and then a max pooling. Okay. Now, over here as a resultant which comes down has 512 such channels across the volume which is coming out over there, and then in total if you look into the total number of neurons present over there. So, that total number of neurons after linearization is 25088, 25,088 such neurons. So, this in the first fully connected layer is what connects it down to 4096 neurons. Then we have a dropout which uses a 50% dropout ratio over here. These 4096 neurons are again connected down to 4096 neurons, and then you have a 50% dropout coming down over here, and finally these 4096 neurons are again connected down to 1000 neurons. Now, this is your VGGNet in the classical style. However, the kind of data which we are using in CFAT 10 that is a 10 class problem. So, if you just have 1000 neurons over there, it does not make sense because it will not be learning. For 990 neurons, it will not have any data to train it down because those classes are just missing over there. So, in order to do that, what we are going to do is just a tad bit of modification. This is still untrained, so it does not create any sort of a problem inside over there as well. And for that, what we do is we keep on modifying this one. So, first point is just delete out this last layer over here and then introduce a fully connected connection between 4096 neurons to 10 neurons, and that is what will solve it out. So, that is what is exactly introduced over here, and now if you print your whole network, so you would be able to see that the last layer is now which connects on 4096 neurons onto 10 neurons, and quite simple and sweet solution to this problem. Okay. So, now we have our VGGNet which is modified onto take down and classify up to 10 neurons. Now, with this modified architecture which just classifies it onto 10 classes and not 1000 classes as was in the original ImageNet problem, we need to find out what is the total number of parameters which goes down. So, for that I will be looking into my first layer. So, my first layer basically has 3 cross 3 kernels, and the z direction or the number of channels in that kernel is also 3 because that matches down with the number of channels present down in my input image. Okay. And there are 64 such unique number of kernels which are present over there. So, that makes it 64 into 3 into 3. Okay. Now, with each of these 64 kernels you also have a bias associated with it, and that is this 64 number of biases which comes down. So, this is for my first layer. Okay. So, my second convolution layer will have the input over there has a depth or the number of channels of the input data is 64. The spatial span is 3 and 3 still. So, this becomes 64 into 3 into 3, and I have 64 such number of unique kernels coming down. So, that makes it 64 into 64 into 3 into 3, and I have one bias associated with each of these kernels over there. So, that makes it 64 additional biases, and then this is what is added down. Subsequent to that, I connect down 64 channels onto 128 channels with a 3x3 convolution kernel, and for each channel I have 128 biases. So on and so forth, I can keep on going till I reach down a point over here, which is my end of convolution layers. So beyond that, what I have is a connection of 25088 neurons to 4096 neurons, and for each of in the fully connected layer. So that is the first fully connected layer which comes down. So you have 25088 neurons connected down to 4096 neuron, and each of these 4096 neuron also has one bias coming down over there, and that's this additional 4096 which gets added. Now 4096 neurons are again connected to 4096 neurons, and then you have an additional bias of 4096 number of elements. The final one is which connects on 4096 neurons to 10 neurons, and for each of the neuron you have an additional bias which comes down over here. Now if you take down a total of all of these parameters, this is what it comes down. So that's closely about 134 million parameters. So this is a number. So somewhere over here is your dot, if you would like to put that. So this becomes 134.301514 into 10 power of 6, or 130, roughly about 134 million parameters over there. Now if it was an original VGGNet which has 1000 neurons to which it was mapped, so obviously that would be a larger value. Then instead of this 10 over here, this becomes 1000. The number of biases over here also become 1000. So that's the change which would happen if we move it over to a standard VGGNet for the ImageNet kind of a problem. Now once this is done, my network is completely established. Now what I would like to do is that just copy down my random weights and keep it for my use if I want to do anything. And then typically, as with the earlier examples, I was actually visualizing it out and trying to show you how these things are changing over there. Okay. Now following this, what I do is actually check down if my GPU is available. Now if my GPU is available, then I can get it running and started on the GPU itself. So once having done that, the next is the classical thing, which is to look down into what kind of a problem I am trying to solve. So here the kind of a problem is a classification problem. So the cost function which I am going to use is going to be a classification cost function, and for that purpose we make use of the negative log likelihood cost function over here. And then finally I have my optimizer which is to be used, and this optimizer which I make use of over here is the ADAM optimizer, plain simple ADAM, adaptive momentum optimization over here. Now this solves my part of the loss function and the optimizers which I am supposed to use now. The next part is to look through my network. Okay. So what I do within my training part over there. So till here you had your network defined, the total number of parameters taken down, your GPU availability checked, and then your training and loss functions defined. And the next part is quite straightforward, that you are going to look down through the whole training process. Now the training process is in no way different, and by now you should have been getting used to and accustomed that the best part of all of this is that it's too modular in structure. So you can just have all of these definitions taken down and kept down over there, and based on whatever is your network definition in your net, just changing that definition is what solves the rest of your problems over here. So nothing major to change as such. So over here what I do is I start down my iterations or my number of epochs over there. Within each epoch I just initialize my timer, and then what I do is I start my training data loaders. Now if my GPU is available, then it's typecasted as a CUDA variable so that it's available on the GPU as well, and then after that what I do is I zero down all the gradients within my optimizer, the first step of just zeroing down gradients so that we don't have any residual gradients pumping through the network over there. The next part is doing a feed forward over the network, which comes down over here. Once your feed forward is done, you have these outputs available over there. You can find out your loss function. Now your criterion over here being negative log likelihood, so we needed to take a log softmax transfer function over there as well, and then you can convert and then you can actually find out what is the computed value of the loss between your output and the labels. So whatever thing was predicted over there, with whether it was matching down your labels or not. Okay. So once your loss is there, next we need to find out what is nabla of the loss or nabla of j, or the first derivative of the cost function, and that's what we need, and that's what's computed using the backward operator over here. And finally, once the loss is computed, you need to do your back propagation. So that's with the optimizer dot step running down over there, and then over each batch we are supposed to just sum up what is the total loss coming down, okay. And then the average loss is what is divided by the total batch size, which gives you the standard average loss coming down. And then what you can do is create an array of training loss, so that at every epoch you know exactly how the loss was moving down and what was the loss at the end of every epoch during an epoch of training. Now, once that is done, the next part is to look into the validation, and what we make use of over here is the standard validation set which we have access to. So, this is the test data set which is available over there, which has not been used during the training process. So, what we do is we just run down our data within the test loader part over there, and then if my GPU is available, then typecast it onto my GPU things, and then once the typecasted variable is available in terms of CUDA or available on the GPU memory, I can do a forward pass over the network and then get down whatever is my predicted value of the class which comes down, and that is the result of this max operator coming down over here. Now, once it is predicted down, what I do is just convert it onto my CPU and bring it back over here, such that I can do the rest of the calculations. The rest of the calculation is pretty simple, that I need to compare whatever is my predicted value of the label, whether that is the exact value of the label on the data which I am using over there, and if it is so, then that is correct. So, just take a sum over all of them, and that is going to give me the total number of correct things I have done, and that is out of that is out of the 10,000 samples which are available in my testing data. So, if I divide this by 10,000, I get down my average accuracy coming down over here, and then I just decide to put down my average testing accuracy per epoch in terms of an array which I can use it for subsequent inferencing over there. Now, the next part is pretty simple. So, this is just to plot down your training errors as well as your validation accuracy over there. So, while your training error is expected to go down, your validation accuracy over time is expected to go up as it comes down, and then this just keeps on printing it out. So, now once you train it down, you would see that it does take a significant amount of time. So, an epoch takes roughly like 15 minutes or 17 minutes of time going down over there, and for that reason we had just chosen down only 5 epochs. Now, you need to keep in mind, so networks like AlexNet or LeNets, they are much smaller in size, and then the number of compute which happens down is much smaller, whereas over here you have large number of computes. The total number of parameters which you are learning, the total number of parameters which get updated over there is also large, and it's for this reason that you are going to take down more amount of time. Deeper networks are computationally expensive, but then later on when we get into studying down even more deeper networks like residual networks and others of the like, you will realize that it's not always necessary that you need to have a lot of parameters only if you have a deeper network. It's just by a mathematical scaling of the width of the network, which is also a critical factor in terms of determining the total number of parameters which you have to tune as you go across the network. Now, if you look into it, you start with a training loss initially of 0.02. Within the end of first epoch, it drops down almost to half of it, and then it keeps on steadily declining over there. The accuracy starts roughly at 56%, but you need to keep in mind that when the network was initially started down, and then we had batch updates which were going down. Now, my batch size over here, which I had defined within my loader somewhere over here, is 64. Now, I have 50,000 such samples available, and I am loading those into number of batches which is 64. So, I get down basically 50,000 divided by 64 number of updates happening within each epoch. So, after that many number of updates, so that's roughly 50,000 divided by 64 is about 8,000 of updates which go down over there, and with that many updates happening down within each epoch, you already raise to a accuracy of 56% at the end of the first epoch when it stops training. Okay. Then you go down to the next epoch, and you see at the end of the next epoch you have a jump which is almost 15% above the earlier case, and goes down to about 71%. From there it has a 6% jump going down to 77%, from there a 2% jump to 79%, and then it somewhat comes down to a point of where it might be hitting down saturation. So, this is a point where you can still keep on training, playing around with the learning rate over there, maybe reduce the learning rate, and then you would see this increasing over there. So, what happens down on my loss curve is, my loss curve is still monotonically looking like it is going to decrease significantly, although my accuracy comes down as if it is going to saturate out. However, this is the whole trade off. So, my slope of accuracy increase does not become so high, whereas my errors which are backpropagating and still tuning out my weights are significant. And then what I need to do over here is basically fix down the learning rate such that it keeps on coming down to its actual global minima instead of getting stuck in the local minimas over there. So that's what we had already discussed earlier, and then finally what I do is on my model which has been trained over here, I just copy down my weights and keep them and then try to visualize it out. So my visualization routine is the same as we had done in the earlier case, and the first model is to look down into this first set of convolution layer. So the first convolution layer which connects down your image space onto 64 channels over there. So what I do technically is each is a 3x3 kernel, and that's why you have these 3x3 patches, and then you have 1, 2, 3, 4, 5, 6, 7, 8 patches over here, and similarly you have 8 number of rows coming down as well, and that makes it total number of 64 patches, which corresponds to 64 unique kernels which has been learnt by the first convolution layer over there, and each takes in RGB or 3 channel inputs. Okay. Now from there these were the weights which were at the start of the training, or what was randomly available down to everyone for use. Now this is what happens at the end of training of all of these 5 epochs, by the time it has reached almost till 80% of an accuracy. Now it still does not quite make sense, because you are not able to see down figures. If you had larger size kernels, you might be able to make sense of what kind of wavelets these are, but these are some sort of feature extractors, quite similar to convolutional feature extraction with wavelets, which are quite useful, and these exist on the color space as well. So but looking down into my weights, I can see that there have been decays. There have been certain number of weights which had a different kind of a change, so they were not shades of the same color which were changing, but they actually end up getting a different color as well. So that's what we have over here in this one, in this one, in this one, this one, and then you see significant amount of change coming down, and then this in total makes down that the change which happens, although you don't see it evidently in terms of getting down a very crisper kind of a structure, but although the structure is not very crisp and geometrically what can be defined down, but what it learns is necessary in order to actually wire down all the neurons which are characteristic of a certain kind of an object, and that's the reason why these group of neurons would be helping you in classifying the whole process. So later on in the lectures when we go down, we will also be looking down how to track down on how these neuron activations are, and then what is the area from where a certain kind of an activation is coming down, in order to find out what regions of an image are what are very significant of a particular kind of a class of object, and can we actually go down to understanding from a classification problem like which attributes of an image as they appear visually are what is important and significant in order to classify it belonging to that class. Now this is for my first layer over here. Then I go into looking down into my second convolution layer, and what I choose over here is to take down my first kernel of my second convolution layer. Okay. Now on my first kernel of my second convolution layer, I have 64 channel output which comes down from my earlier convolution layer, and all of these 64 are mapped down to a kernel over here. So there is technically this kernel is a 64 cross 3 cross 3 in size, and what I choose to do is I take down one of these kernels, or the first kernel over here, and then I just display each of these channels as individual blocks over here. So that's why you see them in grayscale shades over here. So there are 1, 2, 3, 4, 5, 6, 7, 8 of them, and there are 8 rows over there, and each of these is a 3 cross 3. That's for the purpose of visualization. So this is my initially randomized things. This is what comes down after training over 5 epochs, and then if you look into our changes or the differences between them, then this is the kind of difference which comes down. So all of them have been exposed to certain kind of a thing, and in fact for a lot of them you do see a gradient kind of a behavior. So this is where there are almost horizontal gradients coming in to play down a significant role in how they are changing. This is where you have some sort of a vertical gradient as well. So these in total is what happens down when training it down with a VGGNet for the first few layers, and although it takes a lot of time, and then it does have a lot of parameters and subsequently the number of computations which you do, but it's always nonetheless fine. And one of these models is what was a ruling model for a longer period of time. You have other options of going down to a VGG19 as well, so that's up to your exploration. So I leave it up to you. What you need to basically change is go into the documentation of torch vision and look into your models part over there, and then once you have it, so what you can change is here where you are just referencing it out. So if you want to go down with the VGG19, you can just write it as 19. You go down with any other models available over there, you can just pull and do. So, in the subsequent ones where we do some of these very standard models and trying to understand their implementation issues, while we have also already covered down their theory aspects over there, we will be getting you into details of how to recall over there and how to modify. And these are all models, remember, which are not trained initially. These were all randomly initialized and then available from scratch. Whereas on the models over there, on the standard release library, you also have trained models, which means that they have already been trained by ImageNet for a large number of epochs. By the time they reached on the saturation accuracy of somewhere more than 90%, so somewhere about 95-97% over there, and those models with the trained weights are also kept down for use, and then that's in a later point of time when we go into understanding domain adaptation and transfer learning is where we will be making use of them. So, till then stay tuned, and while we resume back for more deeper networks as well.